Okay, let's move on to operations on radicals, and we'll start with adding or subtracting radicals. What we need to learn about adding or subtracting is if the radicals are alike, you can actually add them. Like here, the radical is square root of 7 in both of these terms. So you could do this two ways. You could just say, well, I've got 2 of these plus 3 of these, and that's going to give me 5 of these. But if you prefer, you can actually factor the square root of 7 out of the two terms. And when you factor square root of 7 out, you get 2 plus 3, which gives you the same thing, 5 times square root of 7. And here's another example. This one, you got 5 of these square roots of xy minus 3 of these square roots of xy plus 1. There's an understood 1 right there. So what you could do is you could factor the square root of xy out of each term and then just write it over here, and then you'd be left with 5 minus 3 plus 1, which is simply 3. So you'd have 3 times the square root of xy. Now on these, if you'll notice, the first one, the radical is square root of 3x, but on the next two, it's square root of 3xy. So we can combine these two, but we can't combine the first one. So we'll just bring the first one down, since it's not a like term. And then on these two, we can factor the square root of 3xy out of that, and we're left with 2 minus 4, and 2 minus 4 is negative 2. So we have 5 times the square root of 3x, and then minus 2 times the square root of 3xy, again because these radicals are not like radicals, so therefore you're not able to combine those two terms. So that would be your final answer. Sometimes you might think that you have unlike radicals, but then with a little bit of work you find out that they're actually like radicals. So actually on these 3 radicals, on the square root of 75x, I can actually write the 75x as 25 times 3x, and then the 48x I can write as 16 times 3x, and then the 27x I can write as 9 times 3x. Now since 25 is a perfect square, I can pull it out of the radical as 5, because the square root of 25 is 5. And I can do the same thing with 16. The square root of 16 is 4, so I can pull it out of the radical. And then the square root of 9 is 3, so I can pull the 3 out right here. And then that's going to give me 10 times the square root of 3x. And then multiply here, you get minus 36 times the square root of 3x. And then bring down the third term, 3 times the square root of 3x. And now all your radicals are like radicals, and so we can just factor out the radical and then figure out what 10 minus 36 plus 3 equals, which is negative 23. So we have negative 23 times the square root of 3x. So here we have another one that it appears that they're unlike radicals, but let's simplify each of these radicals first and see what happens. Now I can write 98 as 49 times 2, and then x squared, I know I can take the square root of x squared, so let's put that with the 49, and then I'll put the y over here. And then let's look at the next one. The next one, I can write 32 as 16 times 2, so that's 16 times 2, and then I'll put the x to the 4th right here and put the y over here. So I kind of like to keep the factors that I can take the root of together, and then those that I can't take the root of, I also keep those together. So here I have I can take the root of 49 in x squared. The square root of that would be 7x, so I'll pull that out right here. And then the 16, I can take the square root of that and get 4, and then the square root of x to the 4th is x squared, so I'll bring that out here. And now notice that that leaves me with 2y left in the first radical and 2y left in the second radical, so therefore I have like radicals now. Okay, let's finish the multiplication here. 5x times 7x would give me 35x squared, and 3 times 4x squared would give me 12x squared. And I'm subtracting these, so what I can do is I can factor out the radical portion out of those, and that's going to leave me with 35x squared minus 12x squared, and we know how to do that. We just do 35 minus 12, and that's 23, so I get 23x squared times the square root of 2y. Now over here I've got a cube root, so I've got the cube root of 81x to the 6th minus the cube root of 192x to the 6th. Now I know I can take the cube root of x to the 6th out because the cube root of x to the 6th is x squared, but let's see if we can think of a number, a factor of 81 that's perfect cube. So if I write 81 times 27, then times 3, I mean 27 times 3, I know I can take the cube root of 27 out and get 3. And then over here I can write 192 as 64 times 3, and again I can take the cube root of 64 out because that's 4. And so now let's remove the factors that are perfect cubes from the radical. So the cube root of 27 is 3, and the cube root of x to the 6 is x squared, and that leaves me with the square root of 3 inside. And then here the cube root of 64 is 4, and the cube root of x to the 6 is x squared, and that leaves me with square root of 3 on the inside there. So now I can factor the square root of 3 out, and then just figure out what is 3x squared minus 4x squared, and that's just minus 1x squared. So the answer would just be minus x squared times the square root of 3. So now we'll move on to multiplication of radicals. Let's start with a couple of simple ones. If you have square root of 8 times square root of 12, I can write that as square root of 8 times 12 using my radical property. And then 8 times 12 is 96. Well, then I can simplify that because I can write 96 as 16 times 6. So I can actually break this up into the square root of 16 times the square root of 6. And then I know the square root of 16 is 4, so my final answer would be 4 times the square root of 6. Now over here, anytime you're multiplying the square root of something times itself, that's actually just going to eliminate the radical, and you'll just get what's in the radical. But let me show you why. If you take the square root of 5x times square root of 5x, that would be the square root of 5x times 5x, which is the square root of 25x squared, which is actually 5 times the square root of x squared, which would be 5x. So actually you could kind of add a little property here. So anytime you have the square root of a times the square root of a, that's going to equal just a. And so actually, knowing that property now, I could have just said the square root of 5x times the square root of 5x is 5x. Now, I will tell you that some texts will teach this where when they take the square root of something squared, they'll write that as the absolute value of x when it's a variable. So they'll write that as 5 times the absolute value of x rather than 5x. And that is in case the number you're squaring is a negative. But I'm not going to worry about that here. But we'll just assume that all the variables are positive when I do the operations. On this one, you have square root of 2x times square root of 18y, and you can multiply those together inside the radical, and you get square root of 36x squared y, and the square root of 36 is 6, the square root of x squared is x, and the y stays in the radical, so you just get 6x times the square root of y. Over here you get square root of 20xy to the 4th times square root of 5xy cubed, and when you multiply those together in the radical, you'll get 100x squared, y to the 7th. Actually, you get 100x squared y to the 7th, but I can take the y to the 7th and write it as y to the 6th times y, and then that way I can take the square root of the y to the 6th, but this y would stay in the radical. So I get 100 x squared y to the 6th, and the square root of 100 is 10, the square root of x squared is x, the square root of y to the 6th is y cubed. So I have 10x y cubed times the square root of y. Now over here I have fourth root radicals, and of course I can't use the property that I'm using if I have a fourth root radical times a cube root radical. That's a bit more complicated, but since these are both fourth root radicals, I can multiply them the same way I've multiplied the last examples. So this will be the fourth root of 8 times 8, which is 64, and then x cubed times x is x to the fourth, and then y times y to the fourth is y to the fifth. So now I need a factor of 64 that I can take the fourth root of, which would be 16, because I know the fourth root of 16 is 2. And then I know I can take the fourth root of x to the fourth. I can't take the fourth root of y to the fifth, but I can take the fourth root of y to the fourth. So I'm going to write y to the fourth as, write y to the fifth as y to the fourth times y. And the 4 is because I had to break the 64 up into 16 times 4. So the 4 stays there. So now take the fourth root of 16, which is 2. The fourth root of x to the fourth is x. The fourth root of y to the fourth is y. So I have 2xy on the outside, and then the fourth root of 4y remains in the radical. Here's a similar problem where you're multiplying a cube root times a cube root, and when you multiply that together you get cube root of x to the 8th y. And so I'm going to write that. I know I can take the cube root of 8, so I'll leave that, and then x to the 8th I'm going to write it as x to the 6th times x squared, and then I'll put the x squared over here with the y because I can't take the cube root of these factors. So the cube root of 8 is 2, the cube root of x to the 6 is x squared, so I have 2x squared times the cube root of x squared y. If I have binomials with radicals, I just use the FOIL method. So here I can multiply first times first, 3 times 5, which is going to give me 15. And then the outer product, 3 times minus 2 square root of x, is going to give me minus 6 square root of x. Then the inner product, 2 square root of x times 5, is going to give me 10 square root of x. And then if I multiply the last term times the last term, I have 2 times minus 2, which is negative 4. And then remember, when I have square root of x times square root of x, that's just going to be x. Now, simplifying like terms here, minus 6 square root of x plus 10 square root of x, I can add those terms and get 4 square root of x. So I have 15 plus 4 square root of x minus 4x for the answer. This last example is to lead you into the next section for rationalization. Here I have two conjugates, 5 plus 3 square root of 7 times 5 minus 3 square root of 7. Notice these are exactly the same except for the signs. Now I can do it with the FOIL method, 5 times 5, 5 times minus 3 square root of 7, 3 square root of 7 times 5, and then 3 square root of 7 times minus 3 square root of 7. And it'll give me 25 minus 15 square root of 7 plus 15 square root of 7. So notice that these middle terms will cancel, and then over here I'll have minus 9 times 7, and so I'll get 25 plus 0 for the middle terms minus 63, which is negative 38. Now this is actually a special product of conjugates, and it turns out that anytime you multiply, and you know this from earlier polynomials, a plus b times a minus b, you actually get a squared minus b squared. So I actually could have done this problem by saying 5 plus 3 square root of 7 times 5 minus 3 square root of 7 is simply 5 squared minus 3 square root of 7 squared, and 5 squared is 25, and then when I square the 3 times square root of 7, 3 squared is 9, and when you square square root of 7 you get 7, so that's going to be 25 minus 63, which is negative 38. And like I said, these pairs are actually called conjugate pairs, and they're used when we rationalize radicals when we're doing the division operations. And I'm going to do the division operations in the next video.